Thank you very much. Good afternoon, everyone. Thank you for attending this journal club. I am now going to try to make the slides work. I hope this works. Right, that looks okay to me. I hope it looks okay to everyone else. If it doesn't, then somebody should shout out. So, here is an overview then of the summary that I'll give of the paper. I'll talk a little bit about matched case control studies and give the example of the EPIC study in particular. Then I'll talk about hospital imputation. I'll give some results, a simulation study, and from the actual EPIC study itself, and then end with some conclusions. So matched case control studies. Well, case control studies in general are used to investigate the association between a disease and some putative risk factors. They involve sampling a set of disease people, these are the cases, and a set of corresponding undiseased individuals, these are the controls. And then we compare the average exposure in the cases with the average in the control. And if, for example, we find that the average exposure is higher in the cases than in the control, that might lead us to suspect that the risk factor is causing the disease. However, as in all observational studies, confounding can be a problem. And the way that confounding is dealt with in a matched study is that each of the cases is with one or more controls on a subset of the confounders, and then conditional logistic regression is used to adjust for all the other confounders that haven't been matched on. So an example of a matched case control study is one which was nested within the EPIC Norfolk cohort. Now, participants in the Norfolk cohort were given, at the time of recruitment, a food diary to complete. And during the course of 7 days, they wrote in this diary everything that they ate. And then the cohort was followed up for about 10 years, and during that time there were 318 cases of colorectal cancer. At the end of the study, each of these cases was matched with 4 controls on sex, age, and date of recruitment. And then conditional logistic regression, or CLR, was used to estimate the association between the risk factor of interest, which is fiber intake, and colorectal cancer, adjusting for confounders that haven't been matched on. Now, the problem in this study and in nested case control studies more generally is that there are missing data, and these missing data in possibly the exposures and the confounders complicate the analysis. So what we could do is simply fit the conditional logistic regression model just to the individuals with no missing data. But this so-called complete case analysis can be inefficient. So, for example, in the EPIC study, it excludes 25% of the cases and 39% of the controls. Other more efficient methods have been proposed, but they have limitations. So many of them assume that there's only one partially observed covariate, and many of them require bespoke computer code. And what we wanted to do was to propose a method which could be used in just standard software and could handle multiple partially observed covariates. And an obvious choice to us seemed to be multiple imputation. But we wanted to work out how to do multiple imputation in a principled fashion. So we think multiple imputation is good because it's many researchers are familiar with it, software is readily available, it allows for multiple partially observed covariates, and it also allows you to use information on variables which are not actually confounders, but which are predictive of missing values in the confounders. So these are auxiliary variables, and there are good reasons for doing that. So notation then, I'm going to use D as an indicator of disease status. So D equals 1 for cases, 0 for controls. XCAT and XCON are the partially observed covariates, categorical here I'm going to assume that there are no fully observed covariates, but if there were, then they could be conditioned on in the imputation model. As I say, the analysis model is a logistic regression of disease status on the covariates, and we will be considering 3 imputation models. Each of these imputation models is a model for the joint distribution of covariates given the active variable and the disease status. And for simplicity, I'm going to assume that the categorical variables are all binary. Slide number 7, please. So for those of you who are less familiar with multiple imputation, here is a quick overview. So the idea is that you have an incomplete data set and you fill in the missing values by sampling values from some appropriate distribution. I'll come back to that in a moment. In this way, we create one imputed data set. So this is a data set where there are no missing values. And we do that not just once, but multiple times, say capital N times. And then we fit the analysis model, the conditional logistic regression, to each of the imputed data sets separately, and then we combine the parameter and variance estimators to get an overall set of parameter estimates and variance estimates using Rubin's rule. So we need to sample the missing values then from some appropriate distribution. And how do we do that? Well, a commonly used method is to specify a Bayesian model for the distribution of the partially observed variable given the fully observed variables, and to use non-informative priors. And you fit that model to the observed data and then sample values for the missing variables from their posterior predictive distribution. And this is called joint model MI. So the first of the 3 imputation models that we considered was a restricted general location, an RGL model. This is a model which assumes that the categorical variables, they are log linear model, conditional on the fully observed variables, and then conditional on all of those variables, the continuous variables follow a normal distribution. Now this model is interesting because it's compatible with the analysis model. When I say compatible, what I mean is that there exists a model for the joint distribution of the covariates and the disease status, which implies that the conditional distribution of the covariates given the disease status is actually the RGL model, and the conditional distribution of the disease status given the covariate is the conditional logistic regression model. So in other words, there's no contradiction in assuming the analysis model and the imputation model. So that's the RGL model, and we could draw values for the missing variables from their posterior predictive distribution implied by this RGL model and the observed data. And that was a joint model MI using the RGL model. You could do that. You could use specialist Bayesian modeling software to do this, but we think that we want to come up with methods which could be used by statisticians who's happy using their preferred statistical package like R or Stata, but doesn't want to use specialist Bayesian modeling software. So, slide 9 now. So, instead of using joint model MI, we turned to MI by full conditional specification, which is FCS MI, or also known as MICE. And this method is available in many statistical packages like R and Stata. Now, FCS MI is somewhat like a Gibbs sampler. The way it works is that you specify a model for the distribution of each partially observed variable given all the other variables. And that's called the conditional model. And then you iteratively cycle through the partially observed variable, sampling the missing values of the current variable using its conditional model. And in this case, we use the default option in most of the software. So that means that the conditional model for each continuous variable is just a linear regression, and for each binary variable, it's a Now, as well as being the default, these conditionals are interesting because they are of the form which is implied by the restricted general location, general location model. And the reason why that is interesting is because of a result obtained by Liu, Gelman, and others a few years ago. They showed that this implied that when you use FCSMI in this way, the distribution of the imputed values that you get converges as the sample size increases to the distribution of the imputed values that you would have had if you had used joint model MI. So in other words, informally speaking, this procedure is asymptotically equivalent to using joint model MI under the RGL model. Now, slide number 10. So the other two methods, the other two imputation models that we considered, are not compatible with the analysis model, but they have the advantage of allowing joint MI in standard software. And we thought that maybe by using joint model MI instead of FCSMI, these methods might be more effective. So the first of these two imputation models is a normal model, and this assumes that the covariates are normally distributed given the matching variables and disease status. This model is commonly used in practice, it's just for multiple imputation in general, but not everyone likes it because obviously binary variables can't have a normal distribution. So that leads us on to the third of the imputation models, which is the latent normal model. This is like the normal model, but it replaces each binary variable by a continuous variable, a latent continuous variable, which when it is positive implies that the binary variable is 1, and when it's negative that the binary variable is 0. So now I'm going to present the results, some of the results from the simulation study. So each of 1,000 simulated data sets was generated from the RGL model. We had 2 matching variables and 3 covariates. 2 of them continuous, 1 binary, and of those 3, 2 were partially observed. I'm going to show you the results when we have 500 matched data sets, each of which just contained 1 control. And we have 25% missing data in each of the 2 partially observed variables. Slide number 12, please. So this table shows the results from the simulation study for the log odds ratios of the 2 partially observed covariates. And you can see the first row shows that the true values of the log odds ratios are 0.42 and 0.33. The second row are the results from the complete data analysis. This is where we analyze the data before imposing missingness on it. Remember, this is a simulation study, so we know what the missing values are. You can see that the log odds ratio estimates are approximately unbiased, and you can see what the standard errors are. The third row shows the results when you restrict the analysis just to the complete cases, just to the people with no missing data. There's a hint there of a bit of finite sample bias in one of the log odds ratios, but it's not very big. More importantly, you can see that the standard errors have increased quite considerably, showing the loss of information from excluding from the missing data. The next 3 rows show the results from the 3 imputation methods. They're approximately unbiased, and you can see that the standard errors now are much closer to those from the complete data analysis than from the complete case analysis, showing that by carrying out multiple imputation, we have managed to recover a lot of the lost information. Okay, slide 13, please. So here are the results from the analysis of the EPIC data themselves. So from the complete case analysis, we get an estimated log odds ratio of minus 0.2 with that standard error of 0.12. or strictly speaking, that eating more fiber is associated with a slightly lower risk of colorectal cancer, although it's not significant. And the results from the three multiple imputation methods were all quite similar. And importantly, you can see that the standard error is now 0.104. So again, we've managed to recover information from the incomplete cases by using multiple imputation. Slide 14, please. So I presented then three imputation methods, and all of these three imputation methods have involved imputation models, which are models for the joint distribution of the covariates given the disease status and the matching variables. But sometimes conditioning on the matching variables in this way might not be feasible or might not be desired. This could be, for example, because matching is on postcode or family or GP surgery, some other categorical variable with many levels. And if you try to condition on that variable, you would need a lot of parameters in the model, and that could cause problems. Second reason is that the analyst might not have been given data on the matching variables, perhaps for confidentiality reasons. And the third reason is that the analyst may prefer not to model the effect of the matching variable, arguing that they used conditional logistic regression in order not to have to make assumptions about the effect of the matching variables on the disease risk, and hence they don't want to model the effect of X on the covariates either. And so in the paper we described three analogous imputation methods which don't make use of the matching variable. What they do instead to impute using models which are models for the joint distribution of all of the covariates on all of the individuals in the matched set, conditional on the disease statuses of the individuals in the matched set. Slide 15, please. So, some conclusions then. We think that multiple imputation is a simple, versatile solution to the problem of missing data in matched case control studies. And the proposed method impute the missing values using both the matching variable and methods that avoid doing this. All of the methods can be applied in standard software, and in the simulation studies we found that all of the methods appear to work well, and we think that you could use any of them. Not surprisingly, imputation using the matching variables was more efficient than not using those variables, because you're using more information. And FCS-MI nearly always gave the least biased estimate, less biased than the normal and the latent normal. But perhaps this is not terribly surprising since the data were actually generated from the RGL model. On the other hand, we found that using normal or latent normal MI was sometimes a little bit more efficient than FCS-MI, as we had anticipated it might be. In fact, just to flag up some later work that I did with Rachel Hughes at Bristol University, we showed that joint model MI is indeed more efficient than FCS-MI using conditional models implied by the joint model. But that this efficiency gain is, as we found in the simulation study that I presented here, the efficiency gain is usually pretty small, unless associations between variables are very strong. And moreover, FCS-MI is actually, we found, more robust than this specification of the joint model than is joint model MI. Slide 16, please. So here are the references, and thank you very much for listening.
Perfect. Thank you so much. We really appreciate that. Dr. Daniels, would you like to go ahead and take over? I have your slides up on the slides up right now.
Okay, hi. So can everybody hear me?
Yes. Yes.
Okay, good. Yeah, right. So if I understood, I'm not in charge of advancing the slides. you will do that. Is that right?
Correct. I will take care of that for you.
Okay, thank you very much. Okay, so I'm now on slide 2. So first of all, of course, congratulations to Sean and to Ruth for this very nice paper. Maybe it hasn't been mentioned in this general club yet, but I understand that this paper won an award for the best paper appearing in biometrics, or one of the best papers appearing in biometrics a few years ago, and of course this is very well deserved, this award. I'm sure everybody would agree. So I just, there's no need for me to summarize the paper because of course Sean has done that, but I felt that the paper gave us. So I thought the paper started with a very thorough overview of the current state of affairs, how missing data are handled in matched case control studies, and that overview made a compelling case for the need for more efficient and flexible methods than were currently being used. And that it also convinced me that the matched case control study was really something that deserves special attention. I mean, sometimes one can get the impression when you see another paper on multiple imputation but applies to X, Y, or Z, that it's just multiple imputation. Why does there need to be a special paper on this particular situation? But of course, the introduction to the paper made it convinced me that this was indeed a valid thing to worry about. And if I've understood it, the matching aspect maybe more than the case control aspect that really requires special attention, but we'll come back to that. And then the paper, of course, that Sean has now summarized very nicely, proposes 2 main ways forward, and then there are 3 options in each of those 2 main ways forward, and obviously both based on multiple imputation. But the first way in which they use multiple imputation is to use the matching variables in the imputation model, and then the second way forward is instead not to use the matching variables, or indeed sometimes the matching variables might not be available, and therefore to have an imputation model that includes a random effect for the matched set. And then of course they compare these proposals in some very nice simulations, and then on the EPIC North study. And the take-home message seems to be that you need to do something sensible, i.e. one of these 6 options, but it maybe doesn't matter a huge amount which of those 6 options you choose. So I thought I would just make a few brief remarks to get our discussion started. So I'm now on slide 3. So yes, as I said, it seemed to me that matching was the issue that really needed special attention here, rather than the fact that a case control study is an outcome-driven sampling design. I may be wrong there, so I think my first question would be, is this a fair summary of the situation? And my feeling is that matched studies often seem to be susceptible to slogans. So I advance into the next frame to show an example of these kinds of slogans that you must reflect the design in the analysis when you have a matched study. And I'm sure that, well, if I advance again, we get another slogan, do not break the matching, and this is mentioned in the paper by Sean and Ruth. And of course, these slogans they have a good justification. I'm not trying to suggest that they're not justified. But sometimes it seems to me from a point of ignorance that match studies often come with this baggage of lots of slogans that one must not do this, one must do this. And it's sometimes the message as to why these things are important is lost, perhaps because they're in an old paper that people have not read, certainly that I haven't read. So advancing to the next frame once more. Yes, thank you. So another question, if this were a face-to-face seminar, I think I the other way around. Maybe it's less of a concern or more of a concern. I just thought maybe some elaboration on that would be helpful from my understanding at least. And then going on to slide 4, from the discussion on model specification, which the author thinks he did more simulations on this in the supplementary material. I got the impression that model specification was in their view a greater concern for the matching variables approach than the match set approach. So first I wondered if we could get confirmation whether that was indeed the case. But then also, if that is the case, then is that really a fair conclusion? Because it seems that one could make an incorrect assumption about the distribution of the random effects in the match set approach, and perhaps that could be as severe as getting the model conditional on S, the matching variable incorrect. But again, perhaps I've misunderstood. So I would be interested to know if Sean has any thoughts on that. And then finally going on to my slide 5, my final slide. As always, one thinks, what are the extensions that could perhaps be made here? So, for example, would it be possible to, would it be possible and would it be a good idea to extend this work to match case cohort studies? In other words, where you have a time to event outcome, but otherwise a similar situation to a nested case control study. And indeed, are there other situations involving matching where this work or some extension of it might also be relevant? I mean, I think of other places where there is some matching in the design or the analysis, things like propensity score matching. And to me, that doesn't immediately seem to suffer from any of the same issues that this work was addressing. But again, having Sean's thoughts on that would be extremely nice. So yes, that's all I was going to say, and hope it just gets a bit of a discussion that started that point. Thank you.
Thank you very much. So I think what would be best is maybe to have Sean answer some of the questions you posed in your.
Okay then, thank you very much. Maybe if you go back to the beginning again, and I'll
Sure, not a problem. 1 minute here. So we've got her first slide up on the screen right now.
So the next slide, I think.
Yep.
Thank you.
Is the sticker right here?
Yeah, I think the matching issue is the most fundamental to the paper. I do agree with that. Next slide, please. And the next one.
Oh, sorry. There you go.
Right, okay. Pros and cons of breaking the matching and how they're different. Okay. Right, well, pros and cons of breaking the matching in general. So the usual argument goes like this. Let's see if I can reconstruct this. So the advantages of breaking the matching are that you can gain efficiency through modeling the confounder effects by using logistic regression, unconditional logistic regression, rather than using conditional logistic regression. The other advantage or the advantage of breaking the matching is that if you're not using multiple imputation and you're going to do a complete case analysis, then what happens when you use conditional logistic regression is that if you've got, say, a case that's matched in a set with, let's say, 2 controls, and the case is incomplete, so has some missing data, then you exclude the case, and the result of excluding the case is that there's no one to compare the 2 controls with. And so effectively, although you didn't want to exclude the 2 controls, you do end up excluding them. Whereas if you break the matching, you can keep those 2 controls in the analysis and therefore use data on those controls. So those I think are possibly the main reasons for breaking the matching. The disadvantages are that you may not be adjusting the confounding properly unless your attempt to model the confounder effect is successful. That is, you correctly specify your models. And if you don't account for the matching at all, then the result is that you get bias towards the null and loss of power. So it's not that you can find effects that aren't really there, but it's just that you lose power. Another reason for not wanting to break the matching, well, I suppose the reason why you did matching in the first place, you did it in the design, was to actually avoid having to model the confounder effect. And so to then, just not do the analysis in a way which takes advantage of that just seems perhaps a shame, really. There is actually, I suppose, another reason to do matching, which is to do with gaining efficiency. And in that case, it can be okay to break the matching. And I should mention, of course, that another reason for doing matching is because you're matching on something like family or geographical area, postcode, as I put it. And in that case, it will be difficult to model those effects. Right. Okay, so you asked how the incompleteness of the data affects these arguments. Well, I suppose the MI using matching variables very deliberately breaks the matching in order to impute the missing data, but then restores the matching for the analysis. Sorry, I'm getting a little bit lost here. As I said, one of the incentives for breaking the matching is to be able to include individuals with complete data in the complete case analysis who would otherwise be excluded because perhaps their controls and their matching case have missing data. Well, if you've got multiple imputation, then of course that argument no longer applies. You've got less incentive to break the matching. Okay, so that's that one. I hope that goes some way to answering your question.
Yes, thank you. That was very clear.
Oh, good. Thank you. So next slide. One could get the impression that model misspecification is of greater concern for the matching variables. Well, that's certainly what I anticipated when I started the work. I did think the matched set approach would be less susceptible to problems of misspecification. However, I don't think we actually showed that in the simulation study. So we did have these supplementary simulation studies where we had misspecification, but we didn't really find if I remember correctly, we didn't actually find one method was more robust than the other. Yes, the distribution about the assumption about the random effect in the matched set approach. Well, that's a very good question. It's a really good question. To be honest, I'm not quite sure how important that would be. It could be important, it may be less important. I remember an article by Charles McCulloch a few years ago, maybe 2010-ish, where he discussed how much the normality assumption matters for various different research aims. And in this case, the most relevant research aim is that of predicting the individual random effects when you're fitting a generalized linear model, a generalized linear mixed model to a set of data. And it seems to me that predicting individual random effects is what's going to matter when you're doing imputation here. He says in that article that it doesn't actually, the misspecification of the random effects distribution doesn't actually matter for predicting individual random effects. However, in terms of estimating the distribution of the random effects, it does matter. So obviously, if you assume that the random effects have a normal distribution and you estimate the random effects, then you expect it to look like a normal distribution, and indeed it does. And I think that might actually be a problem. So potentially, violation of the normality assumption that we've assumed, that could cause problems for MI using SET. So although I've made this argument that I think it'll be more robust than the other method, MI using matching variables, I'm not absolutely sure that's true. It might be true, I'm not sure. There's another paper, actually it's included in the review at the beginning of our paper, paper by, Sinner, 2005, and they consider just a single partially observed variable, and they do multiple imputation using a Bayesian model with a random effects distribution, so like our MI using matched set approach. But instead of assuming a normal distribution for the random effects, they have a Dirichlet process prior, so they don't have to assume normality. Unfortunately, it would have been so nice to have seen the comparison in their paper, but actually they never actually present results for the direct comparison of their model with the corresponding model that assumes normality. Right, next question. So next slide, please. Extensions of matched case cohort studies and survival. I'm not entirely sure what you mean here, but Ruth here has done some work, it's not published yet, some work with me and some others on how to do MI for both nested case control studies, which are a particular type of matched case control study, in which each case is matched to a number of controls, and the controls are chosen as being people who are still at risk at the time that the case fails. And now, this method, I don't see this method as being an extension of what we've been talking about in this paper. Instead, what that method does is it involves using techniques which were originally designed for doing multiple imputation of partially observed covariate in a Cox model, so as you say, for a survival outcome. Ruth's also done work on multiple imputation for case cohort studies, including stratified studies, but again, the analysis is to do with, the analysis model itself is a Cox regression, and there's no matching there. So the next slide, oh yes, other situations where, so you talked about propensity scores. This would be when you're interested in looking at an association between treatment and outcome, or the effect of treatment on an outcome, and you've got confounding because it's an observational study and people aren't randomly assigned to treatment. Right, okay. Well, in this case, where the matching is on the propensity score, then I suppose you could carry out multiple imputation, where you'd include in the imputation model the variables which we used to actually calculate the propensity score. So the variables in the propensity score model. Or, alternatively, you could include in the imputation model the propensity score itself. So it's the former, the way you include all of the variables in the propensity score model, that should be more efficient, but it would involve more modeling of variables. And it should be okay to just include the propensity score in the imputation model, and then you only have to model the effect of one continuous variable, that's the propensity score. And you could use a flexible model for that, so there's less chance of misspecification. It would also be, I suppose, but that would be analogous to the MI using matching variables approach in this paper. But alternatively, I suppose you could use the MI using matched sets approach, where you wouldn't actually use the propensity scores, you just use, as I say, random effect. I think that's all I can really say in response to those questions.
Perfect.
Thank you very much. I guess one difference to propensity score matching is that the matching is done on the basis of the propensity score, which is a function of the covariates. So if you had some missingness in those covariates, you would want to impute them, and then you could do the matching based on the imputed propensity score. Whereas in your situation, the match set already exists. So there is a sort of a conceptual difference there, isn't there?
Oh, I see. Okay, so this, yes. Yes, that's right. Okay. So, yes, so the problem is missing data in the variables in the propensity score model. Right. So that, I hadn't made that connection. That problem has been treated in the literature.
Yeah.
So yeah, there are at least a couple of papers. One of them is by Key from about, I can't remember, 2007, something like that. One of them is by Lee, and yeah, that's about how to do imputation when you've got missing data in a propensity score model.
Oh yeah. But the issues seem to be quite different then, don't they?
Yeah, I think so. I see them as being different.
Yeah. Okay, thank you. That was really very helpful for me. Thank you, Sean, very much.
Yes, thank you. For anybody else on the call, do we have any questions? You can either feel free to chat them over or go ahead and ask them on the phone. Okay. Well, I thank you so much for both of you coming in to participate with our journal club. We really appreciate it. Sorry about the technical issues at the beginning of the phone call. And I think with that being said, if there's no further questions, I think we would be good to end the conversation at this time.
Okay, just before we do, I'd just like to say thank you very much for organising this, and huge thanks to Rian for taking the time and putting the effort into thinking about it.
No, it was my pleasure.
We really appreciate both of you participating and all of your hard work. This was a wonderful conversation and very interesting.
Okay, thank you. Thank you.
Thank you.